Claude, that was funny. Claude, you have to tell the story.
Don't tell.
Okay, I won't tell.
Thank you.
Start. Here we go.
All right. Thank you all for being here, even though we are a little bit behind schedule. I appreciate your patience and your coming to see us anyway. And you are in for a great treat. Bill Ruff has come to us from Canada, long way away, where it's cold, and here it's warm. It's a big change of pace. And so I want to introduce you to him today. So, many of you had the chance to talk with Bill Ruff so far, and one of the first things he asks you when you meet him is, what kind of music do you listen to? And when you think about it, it's like, that's not very ordinary for a mathematician. And the reason is because he was a musician first. He waltzed into mathematics after his music decided that was not for him, and then had a wonderful career in mathematics after that. He won many teaching awards, and he even wrote his own calculus book to go along with his excellent teaching. So there's a lot of wonderful things in his rich career. But now that he's retired, one thing that he was missing while he was doing his mathematics, is his art. The art of creating music, the art of just experiencing the joy and vision and creativity that goes into art as well as into music. And so that's why Bill is here to talk to us today about combining his love of art and music. In fact, it's become such a wonderful thing that even the New York Times interviewed him about his art. So it is my great honor and pleasure to introduce to you Bill Ruff, and I'm so excited to hear your talk.
Thank you so much, Ava. What a beautiful introduction. I have always wanted to come to Morocco, and I've always wanted to have couscous, and today it finally happened. I had my first couscous. It was amazing. I want to thank so much the organizers, Al Hussein, and I think Omar, and Omar helped, and of course, this Omar. For 10 years, this Omar has said to me, Bill, we are going to Morocco. I love Morocco. We're going together. And so here we are, all of us together. All right, this isn't part of the talk, but I want to tell you about it anyway. I'm very interested in complex systems. Stuff that's happening in a very complex way. We try to understand, what is this? I worked with some neuroscientists, and what they do in the neuroscience lab is they attach electrodes to your scalp. With me, it's very easy. And they glue electrodes all over your scalp, and then they feed the brain waves into a machine. And so my friend had all this data, and in 5 minutes you have 1 million data points. And I said, please give me some of that. And so what I wanted to do was to say, what can I do with this information? So I have this electrode and this electrode. I can look, are they talking to each other? Are the brain waves here the same as the brain waves here? Are they correlated between these two? So I wrote a program to look at how connected the areas of our brain are, and I turned that into color and motion. So what you're looking at is a human brain thinking. Possibly about the ABC conjecture. Possibly. So just for 1 second, the patterns in a mind when it's thinking are so rich and so complex. We barely have started to understand how a human brain works. Just for 1 second, look and see a brain thinking. 1 second. Isn't that amazing? I mean, that's just so extraordinary. Okay. But of course, that's not, I want to show you something different. I want to talk about this. Oops, no, go away. One sec. I'll get this right. Okay. Is it there? Yes. Okay, here we go. Because I'm interested in complex systems, at one point, many years ago, I was working with what are called dynamical systems. And I was trying to understand how dynamical systems work. And so I thought, I don't understand. You know what? I'm going to make a picture of this dynamical system. I was using some new mathematics that I'd invented, and to analyze the orbits of a dynamical system, and I thought, I'll make a picture. I took that picture and I showed my friend Ed. Ed is a famous artist in the States. I said, Ed, look, I made this picture. And he looked at me and he said, who painted this? I said, it's not a painting. It's a mathematical depiction of a system. And he couldn't believe it. And so I got very interested in creating pictures of mathematical systems. I'm going to show you a few now. Oh, by the way, so once I figured out how to do some of this, I started making this as artwork, and now I show this art in galleries, and I sell it as well. Prices are available at the end of the talk. So here's an example. That is a portrait of a dynamical system using some mathematics that I invented, which I'll tell you a little bit about in a second. I'm just going to show you a few. These are pictures of dynamical systems. Some simple, some complex. This piece, many of these pieces have been sold, by the way, but what I want you to look at here is to imagine that something mathematical made all of this. There's no editing. One mathematical process made the entire picture, made this line. You can't see it, but this is filled with little lines. You see the little edges here. One mathematical system made that entire picture. Some are very simple. A lot of this is from a show that I had. Many of these pieces are all sold. This piece is from a show in a gallery just north of New York City. One thing can you see any of the lines in here? Can you see lines? Okay, it's actually filled with little lines. And so, what I do with my art, it turns out, of course, many of these systems are chaotic. The best art is just before it reaches the chaotic point. And if you do that, you get these extraordinary patterns of lines sitting inside. I also modify photographs using mathematics. So there's a photograph. These are 3 of my great aunts. This is my family standing in front of a cottage. These are 2 of my friends. Yes, I have friends. So everything here is based on feedback loops. Let's just talk about that for 1 second. There's going to be not too much mathematics in this talk. Alright, but just a little bit. What is a feedback loop? Let's talk for a second. For example, if you have a function like this, so this is 4x times 1 minus x. I think this is the simplest polynomial put up this week. Is it important? And so imagine that we start with an initial value. Let's say the initial value is 1/3. And then we say, what is f of that value? And we get 4 times 1/3 times 1 minus 1/3, which gives us the number, who can tell me? I guess 8/9. So we started with a third, then we got 8/9, and now we do it again. And we get a new number. And so we can keep going on forever. And so we get a long sequence of numbers. So this is an example of actually, this dynamical system is so complicated that we will never understand it. Just that simple operation, we will never understand how this single system works. Okay, so this is what I use. This is how my work is generated. One of the first places this was encountered was when a mathematician named Lorenz was trying to predict the weather. He was trying to figure out how the weather works, so he would put in the weather today, figure out what happened in 1 second, then 2 seconds, then 3 seconds, and keep going and try to figure out the weather next week. And that's what he did. But something strange happened. If he changed what happened on the first day by the tiniest little amount, the weather a week later was completely different. In fact, he thought the computer was wrong. It turned out it was the mathematics. It's incredibly difficult to predict the weather. These are the equations that he was using. But he turned it into a system just like this. He had a function. He put in the weather today. He got the weather the next second. Then he got the weather the second after that. And he found that if he changed this number a tiny bit, the tiniest little bit, actually in the 11th decimal place, then this sequence behaved totally differently. These systems are very hard to predict, and that led to people saying this about the weather. The tiniest error in today's weather can give you completely different forecasts. For this reason, we will never predict the weather more than a week ahead of time. Okay, so my own art, how is it created? Okay, so here's a piece of my art, right here. This is a piece of my art. Let's say it's 30 inches by 30 inches. I have to, in order to do a good job on the printing, it has to be 300 dots an inch. So in every square inch, there are 300 times 300 calculations. So in the whole canvas, there are 81 million separate calculations. So for each of those pieces, I've had to do that much. So this is almost the end of the math part. So the color at every point is determined by how that sequence works. And that uses, a couple more examples. There's another example of one of my dynamical systems made real. And you can see all the intricate work here because these systems are so complex. So, 5 seconds on mathematics. I had the idea to extend the notion of fractal dimension to metric spaces equipped with probability measures. I made a formula based on entropy. And I got a whole family of statistics, D1, D2, D3, D5, D6. I had no idea what they did. But I did discover that the first one seemed to be the fractal dimension. And here they are. Here's the first warp statistic. So, if you take a random sample of numbers between 0 and 1, just take 10,000 numbers that you grab at random from the interval 0, 1, and apply my crazy formula, I kept getting numbers close to 1, and I thought, it can't be an integer. There's no way the answer could be 1, that's impossible. But yes, it was 1, and if you read down, if you know these things, the Cantor, dimension of the Cantor set is this number, and that's what I got with these formulas. Anyway, so I will leave you with that, but there are some complex mathematical formulas behind the art. This is published in a paper. Oh, briefly, I got very interested in the stock market. And I found an amazing thing, that if I plotted the return of stocks against my number, I actually found that with my number, the stocks do better. So this is still an area of investigation. That's partly in the paper I was talking about. Okay, that's the hardest part of the talk. One of the things I love in mathematics is very complicated things can happen from very simple rules. So look at the complexity of that. The rule that generates that is so simple, and yet we get this extraordinary complexity. I'll just show you some details. Okay, I did that. All right. Oh, by the way, how many students are here today? Okay, special welcome to the students. Thank you for coming. Are you mathematics students? Okay. Are there any students who are not in mathematics? Any brave people? Yeah, Omar. Just for 1 second, I'm going to talk about art and mathematics now. So, this is a famous person in mathematics history. This is the teacher of Leonardo da Vinci. His name is Pacioli. And do you know what this is? Can you see it maybe? It's probably too dark. Are you ready? Rhombic cube octahedron. And there it is, sitting in this painting from hundreds of years ago. And this is what Pacioli said. He said, without mathematics, there is no art. I wanted to briefly show you, my friend Jim Stewart wrote the Stewart Calculus book. Does anybody know the James Stewart Calculus book? A few people have used it. Okay, so just to show you that you can get very rich on mathematics. He built this famous house. That's Jim. This is a picture of the outside of his house. He taught calculus, and Jim, because he taught calculus, and he said that everything in calculus is curves. So he wanted everything in the house to be curved. It was a beautiful house. This is my car, parked outside his house. That is the cheapest car ever in his driveway. Every car that... Because, you know, his friends had a lot more money than I did, but just to show you a little bit of the house that he built with calculus, you can see the curves. This house is in Toronto, Canada, and you can see the snow. That's a concert hall. These are some of my works sitting in Jim's house. This is me. And you get the idea. Okay. So now to the main reason for the talk. As I started to make art myself, I wondered, what are artists doing that I'm not doing? Why is there art great? And so, you know, you're a mathematician. And I have images of the art. Let's analyze. Let's analyze their work and see if we can find out what great artists are doing that I'm not doing. So I started to think about contrast. We're going to look now at a painting by Cézanne. Mont Sainte-Victoire. Here's a painting. This is a famous painting, a famous European painting. I want you to look at it for a second. Can you see the sharp line here? Can everybody see that line? Is it sharp enough? Okay, so there's a sharp line here. It's very sharp. Can you see this line here? Can you see that edge? It's not as strong, but still an edge. Over here, how many people can see this edge? Can you see an edge there? Very faint. I can go to every point in the painting and say, how big is the contrast? Is it a sharp edge? Is it a medium edge? Is it a small edge? So I can go, I look here, I look here, I get a number, I look here. How strong is it here? How strong is it here? I can take all those numbers, measure them, and then put them together and make a histogram. Now, the measure, you have to have some kind of measure of the contrast in the picture. It's roughly like this. Every color can be thought of as being made up of red, green, and blue values. So you pull off the red, green, and blue, and you basically estimate the gradient of the red, the gradient of the blue, the gradient, and put them together something like this. That's close to the truth. You actually have to do better than that. But that's close. Anyway, you ready for the histogram? So I take all those numbers. I measure the contrast here. I measure the contrast there. I get, and by the way, you get a million or more numbers. And now you make a histogram. And that's what it looks like for that painting. So this is what I got. And I thought, I don't know, what is it? Is it significant? Is it important? You know, but that's what I got. And I thought, okay, the eye, human beings, we see logarithmically. We feel when you feel touch is logarithmic. Most of the human senses are logarithmic. The ear, you know what decibels are. We measure how loud a sound is logarithmically. So I thought, okay, I will take the logarithm of the contrast. And maybe I might get a bell curve. I had this idea. Maybe I'll get a bell curve. I don't know what will happen. But human beings see logarithmically. That was a reasonable thing to do. I've measured contrast. I have millions of data points. Let's see what happens. So for the painting I just showed you, let's go back. For this painting, this famous Cézanne, it's only worth, 50 million. Are you ready? This is what I got. Okay, this is astonishing. In real life, nobody gets a bell curve like that. It never happens. I have been working with statistics my whole life. You get a bell curve, well, it's roughly the shape of a bell curve. It's sort of close. Not in this case. I want to show you something amazing. Look, this bell curve is perfect. Right out into the tail. Perfect. And the left tail. Look at Cézanne. He painted this bell curve with brushes. Just like that. That is unbelievable that he did that. In fact, when I first got this, I thought, it's impossible. It cannot be this perfect. But I've rewritten all the programs, done it in a million different ways. This is the bell curve that Cézanne got. Now, this is a histogram. What do these points represent? These are the places with very sharp contrasts. What do these points represent? These are the smooth areas. So the smooth areas, and we have lots of middle contrast, and then a few sharp features like so. Okay, so maybe it's a coincidence. Constable, an English painter from the 19th century, a beautiful painting, probably hard to see there. Here's the curve. Degas, his beautiful paintings of ballet dancers. Now at this point I'm excited because I'm going through artist after artist seeing, am I still going to get this curve? There's the painting, beautiful picture, a famous picture actually. And there is Degas. Van Gogh. Who's heard of Van Gogh? Lots of people. Okay? Another famous piece. This is Van Gogh's bell curve. Is it a coincidence? Picasso. Emily Carr, a famous Canadian painter. Oh, sorry, I was too quick. She painted a lot of trees on the west coast of Canada. This is Emily Carr's bell curve. Kiefer, a modern 20th century artist. The Red Sea. Have a look at that for a second. Okay, now watch the bell curve. And now something new has happened. Look at this. There are a little bit too many smooth parts, and there are too few parts where it's highly contrasted. Let's go back to the piece for a second. Do you see that the image is a little bit fuzzy? Right? There's a little bit of fuzziness to the image. It's not as clear as the other images I'm showing you. So according to this technique, it's not as sharp as it should be. I will speak to that artist. Jasper Johns, a famous American artist. Dubuffet. I'll just go through these quickly. Okay. So that's the first part. By the way, a good question here is, does every painting have a bell curve? I will show you some examples shortly, okay, of paintings that fail very badly. Okay, let's talk about looking at a painting. All right, so here's a painting. I could look at the painting like this. I could stand here and look at the painting. I could come back here and look at the painting. You understand? So there are many ways to view this painting from various distances. Question, is there an optimal distance for looking at a painting? A best place to stand? And I thought, you know what? I might be able to detect that. Let's look. A famous piece by Caravaggio. An angel and a man. And this is the bell curve. We have some problems, right? You see that it's incomplete here. Now, for this curve, I'm looking like this at the painting. So I'm right here. I'm looking at the painting like this, and you get that curve, like that. Let's stand back a little further and look at that. If you are very close, you got the first bell curve, too close, a little bit, and one more time. You see, there was a middle place where the bell curve was almost perfect. This is very close to the painting, this is middle, and this is far from the painting. And let's put it all together in a graph. This is very close to the painting. This is standing back a little more, standing back a little more. And you see that there's kind of an optimal place happens around here. When that graph is minimized, that's where you stand. I want to go to the Louvre and tell them where to put the tape. Have the people stand right here. This is the best spot. This is a remarkable painting. In all the paintings I've analyzed, this portrait of Cézanne's wife is one of the most amazing. And the reason is because it looks like that. This painting looks good no matter where you stand. You can stand close, you can stand far away. This painting, if I have this painting here, you view it any way you want. So a question for you, is that an achievement? Has the artist achieved something amazing? Because they have a bell curve across every distance. Let's look at it one more time. There she is. So, according to me, this painting is brilliant at the back of the room. What do you think? Is it good? Here's a graph of Cézanne's works. If we look at the graph, we see that they're minimized somewhere around here. Is the best. By the way, these are amazing curves. His bell curves are incredible. He has the best bell curves of any artist. But you can see that there's a kind of suggestion that the minimum is somewhere right around here in terms of how to view the piece. Okay, let's look at a pointillist artist, Seurat. What did Seurat do? Seurat took his paintbrush and he went, he put little dots of color everywhere, little dots of color. Dot, 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 to make a scene like this one. Now, if you look at the painting, and I've done this, if you put your face here, all you see are dots. And so my thought was, if I stand back, gradually the painting might blur into a bell curve. So there's standing close, standing back further. And you see that if you stand back far enough, it's perfection. Even though the painting is made up of dots, the picture is oh, even better. I have one more. Let's have a pause for artist appreciation. I mean, to create a bell curve with dots that merges together perfectly to form that curve, unbelievable that that could happen. It's time to look at some bad art. It might upset you. You might want to look away. Okay? This is bad art. You probably shouldn't see it. But here's what it looks like. So there's a website called Bad Art. And this is from the website. And here is the curve. Here's another one. I think Omar did this. Omar? And the curve. Now, here's where it gets controversial. Of course, Andy Warhol was a great artist, but his work was more graphical, not painterly. He did more graphical work. This is his Marilyn. That's one of the most famous pieces in American art, and this is the curve. So what we're really getting to here is not whether art is good or bad, but how to capture the style of certain artists, especially European artists in the 19th century. Let's take a look at photography. This man is a very famous photographer. The artistic values of photography are very different than the artistic values of painters, and this is the curve. Another piece, another photograph. Oh, I go too fast. There's the photograph. It's a great photograph. And there's the curve. There was a photographer, Stieglitz, in the late 19th century. He believed that photographs should look like paintings. So if you took a photograph, he wanted it to feel like a painting. And this is a photograph of his. And you can see that it has quite a soft feel with some nice sharp edges, but it has the softness of painting. And I found it interesting that he has almost a bell curve. And it was his belief that photographs should look like paintings. And he has a very good curve. Well, if you stand far enough back, very good values, very close to a bell curve. So now I'm going to help you buy some art. Alright, so let's see how good you are. So, here's your first choice. This is a Chagall. Would you like to buy this Chagall? Or would you like to buy the Canaletto? So what I'm really asking you just for fun is which one of these paintings has a bell curve and which one doesn't? Just think for a second. Is it this one or this one? Okay? This one is a bad one?
Yes.
We burn this painting. And we keep this one.
Yes.
Okay, you ready? Thank you for the talk. Oh, no, just kidding. This is the Chagall. So that painting that you were throwing out is worth about $200 million. Okay, so, you know, I know you would rather do mathematics than have $200 million. I know that. Is it true? And this is the Canaletto. Couple more little things, a little bit technical. How many people have taken stats courses? Who has taken statistics? Quite a few people. Who's taught statistics? Okay. Oh, only a few people. Okay. I don't know if you remember or not. There's the formula for the variance. We take the observations minus the mean, square them, take the average. This is the third moment. We take the cube. Because it's a cube, this quantity can be positive or negative. And then we have the fourth moment, which is always positive. It's the fourth powers. There are a couple of little formulas from statistics called the skewness and the kurtosis. This one measures how wobbly your curve, your distribution is. Is there a long tail this way, or is there a long tail this way? That's the skewness. It can be positive or negative. This one measures how fat the tails are. Are they very fat, or are they too thin, or what are they? Here's an amazing fact. The skewness and kurtosis of a normal distribution are both 0. Okay? So if I have a painting and I check the skewness and kurtosis, I hope to see 0 for both. Let's look. Okay. Can you see the blue dots? Can you see blue dots here? Maybe you should see the optometrist. Blue dots here. Those are pictures I took on vacation. Okay, so all the blue dots are the analysis of pictures that I took while I was on vacation. There they are. You see the black squares. These are the averages for 30 of our greatest artists. This is kurtosis against skewness. This is 0 right here. You see that the great artists are clustered around 0, indicating that they could have perfect bell curves. The skewness and kurtosis are 0. You see my photography is not very good. I'm most often not getting close to 0. So one final thing I wanted to analyze was, we talk about the style of Cézanne. So an artist works in a style, and you see 100 paintings, and you can say, oh, those are all from the same artist. This artist did this one, and this one, and this one, and this one. What is style? What does that mean? So I started thinking about that, and I started plotting some new statistics. These are all of the paintings of Cézanne that I had. Look at how good the fit is. R squared is 0.9668. The paintings of Cézanne, all quite different, all live almost perfectly along this curve. I'm trying to capture the style of a painter. Here's a very, very different artist, Hockney. His work is absolutely different than Cézanne. The curve itself is very different, but the fit is excellent. And his work, if you look at his work, all the pieces look very, very, very different. And yet, they all live beautifully along the same tight curve. So what I'm trying to understand here and trying to get at is to study the style of an artist. Okay? Can you see this picture? Can you see there's a person in there?
Yes.
That person is sitting in the audience. What person is it? Omar. This is Omar. Can you see it?
Yeah.
A little bit? You see the hat?
Yeah.
You see the laugh?
Yeah.
My final slide. Before you buy a piece of art, email me, and I'll check the bell curve for you. Thank you very much. Thank you.
fantastic talk. It's so fun to see all the different artworks. Can we take some questions, please? Well,
Could I see the bell curve of Omar?
Not the belly.
Okay, so he's raised a good question. Can I see the bell curve of Omar? I made that picture of Omar myself, and I will tell you, my art. How great is my art? My art does not have a bell curve. Okay, and I have tried very hard to create images with the correct bell curves. What happens is you adjust here, you adjust here, you adjust here, and then you find that that collides with what you did over here. And it falls apart. I've tried to write algorithms to create the visual bell curves, but you have to create it as a whole. So when an artist is working, they work with a little brush. They work for weeks and months. They smooth, they sharpen edges, they work and work and work. I think it's amazing that they can do this. I cannot yet, as a mathematician, create work that is a bell curve. I cannot say my work is great art. My work, they just don't have bell curves. They just don't. Thanks for asking, Claude. Yes?
You compared your photos from vacation with very good art.
Yes.
Have you compared it with very good photos?
Very good what?
Photos,
not
paintings.
Yes. In general, photographs, I've maybe found 2 or 3 photographs in my life that have bell curves.
No, I'm interested in whether your photos compared to excellent photos have the same skill as photos.
Oh, you think I might be a good photographer?
No, I just want to see if there's a difference between your photos and
I don't have it for you. I don't have it for you. But I like it. I just assumed I was a bad photographer.
I mean, you compared your photos to something else. You didn't compare them to great photos.
I guess the point there was just to say that the standard thing that we see every day, okay, so we look, I see something, I look, I see this image, I look, I see that image. The images that we're seeing every day are not bell curves. What an artist does is giving us an image that is different from everyday experience, which is interesting. I do that.
Okay, so is it possible that the measure that you had for good painting will be different for good pictures, for good photographs? Maybe with a different position because you are using the same measure.
So different, but maybe still good.
Yeah. The measure, yes, that it capture.
Yes.
Maybe it's different for paintings. It's one. And for photograph will be different.
And so I should recognize that there are 2 different, not standards, but 2 different modes. That there's a mode for photographs and a mode for paintings. I've never thought about that. I always think of just paintings. I think because I assume painting is good, and photographs are less, right?
Also, did you go through the centuries and look at art from one? For example, for Europe, it's easier. From one century, from the next century, and just see what happens. We said that in 19th century, it has very good bell curves. But what happens if you take art from, like, say, 13th century?
Yep. So I have done quite a bit of that work in the paper that you'll find on my website. I don't know if I can get to it. Is that here easily? Is it Firefox? Let me just pull it up for a second. Is it coming?
Perhaps.
Maybe not. So on my personal website,
I did some work on this. You looked at different periods.
So yes, on my website, there's a detailed paper with everything in it and the mathematics and an analysis of paintings over the centuries. Okay? And in that paper, you'll find the analysis of hundreds and hundreds of paintings summarized in tables. Okay? So just go to my website, which I had up there. Okay. I put the address here. So the address is bill.rel.com. It's there, under research. Any other questions? Yes?
First, I would like to thank you for this fantastic presentation.
You're so welcome.
It was amazing. So, my question is...
1 second. You know my hearing is very bad.
My question is, if we can extract our system from the image, and if you have already tested this with one of your...
Okay, so it doesn't work with one arm. Is that what you mean?
No. My question is how we can extract our system or our function from the document.
Yeah. Oh.
Is the frequency already yes or no?
I think no.
No.
I think no, but
From 1 inch.
Oh, from 1 inch?
Yes, sir.
So do you mean, can I find it in some part of the photograph?
Yes, sir.
Okay, so he asked an amazing question. He said, so you have a photograph. Maybe 1 inch of it is a bell curve. This is a great question. I can write a program in an hour to do this. Yes. Yes. No, I can, you know what? I'm going to do that. It's such a great question. So instead of looking at the whole photograph, look at just parts of the photograph. This is so easy to do. Yes, thank you. Thank you. I'm not going to give you credit for that idea.
And my second question is, you work usually with real functions or complex functions?
It's all real. Oh, okay. These functions that I'm using.
Yes.
Okay, you want the truth? The truth? Okay. So some of the images that I showed you are dynamical systems from R12, 12-dimensional space to 12-dimensional space. They're not real functions. Okay, they're very complex functions that I've designed to create art. So I often use them. It just ended up that 12 worked out very well. Up to 1, I can tell you why, but there's a reason for 12. Yes, so they're very complex. They're not real functions.
Yes, your title is about the Greek art. And you mentioned paintings, but there are other kind of art, and for example, music. So,
yes,
could you do something the same for music?
You know what? I've always wanted to do something with music. I have not yet attempted it, and I should because I am a musician. You know, I am a musician, and I should try that. I want to tell you a problem with my life. I'm interested in everything, and I have trouble focusing and getting one thing done. And so I wanted to get this right. But I have time now to actually consider this question. Thank you. I will think about that. To do this with music. Any other questions? Yes? Oh, what was I doing? Okay, what does it mean? Measuring. Yes. Okay. So his question is, what does it mean? What am I actually measuring? Let's go up here. You see the edge of this line? Is it very sharp? Okay. It's sharp. I give it a value of 10. That's a number. Okay. You see this edge right here? Not as sharp. I give it a 5. Okay? Let's keep going. Over here, a 4. Here, 0. Do you see the numbers? So for each edge, I assign it a number of how strong the edge is. I get a million numbers, I make the histogram. Does that make sense? Okay.
Yes. So my question is.
So I have very bad hearing.
Can you go the other way around? I mean, from a picture, you can get the. Can you draw a value curve, and then from that curve, identify some potential picture?
to start with the bell curve, yes, I can do that because, okay. So for a given bell curve, can you find pictures that are consistent with that? I don't know if you've noticed, but I haven't talked about the mean or standard deviation, right? I haven't talked about that at all. I just talked about the bell curve. But the mean and standard deviation give you amazing information about the picture. And so I use that information to do what you said. So you want a picture with this mean, this standard deviation. And it turns out every artist is different. Some artists will have a small mean, a big standard deviation, or a small mean and a small standard deviation. And that changes how the picture looks. So I've suppressed all of that. Any other questions? Yes, please.
A question related to that. Can you identify a fake picture?
Okay, can I identify a fake picture? So, can I identify a fake picture? Do you remember the curves I showed you with all the Cézannes? Right? So all the Cézannes live on a curve. If you give me a painting by Cézanne, and it's far off that curve, I think it's likely to be a fake. Okay, so I haven't done this kind of work. Actually, wait now, that's not true. Someone did ask me to use my work to identify a painting. He gave me the painting, and I said, it's not that artist. And you know what? He was very angry with me. Because he was going to make a lot of money with that artist, right? Going to make a lot of money. And I said, no, it doesn't fit. I don't believe that's a real painting by that artist. I forgot that. You know what? I'm not going to do that. It's too scary. Yes? Anyone?
Now it is possible to use computer to paint, right? Now it is possible to use computer for painting.
Yes.
So can you differentiate the painting with computer and the painting with art right now?
Well, I make paintings using computers. So for the last 25 years, I've been making and selling paintings that are made entirely with the computer. My work doesn't have bell curves. I am a failure. Okay, so my work has failed. I'm not ashamed. Yes? What's it? I will come. Oh, you're so welcome.
The artwork you showed us is very art. I see artwork.
You do see it as art?
Yeah.
Hey, wait. I have a vote for my work being art. I have one vote.
One question is that artwork a manifestation of something disability?
Yes, it is. It is, exactly. So he's saying that the art is a manifestation of, to a certain extent, of unpredictability in a dynamical system. Yes. I want to say one thing about that, is that I spend years shaping the dynamical system to something that I personally like. Do you understand? So it's not random. I don't just say, oh, pick a dynamical system, run it, draw it, print it, sell it. It's not like that. I have an idea for a dynamical system. I look at it, and it's terrible. And then I begin to shape it, and change it, and alter it until I get something I really, really like. So I have to say there is some of me there. Do you understand? So,
A second question, sir.
yeah.
My second question is really the better test.
Yes.
So I see that the distance conflict.
Yeah. Yeah.
Distance conflict affects in some sense the match between the
Absolutely, you got it right. Yes.
Are you knowing what you call that
Well, what happened? Okay, so his question is, I had a diagram that talked about how the bell curve changes as you stand back further and further. Okay? So why is it about distance? These eyes are so complicated. You know what they do. As you stand further back, the eyes begin to average information. Right? They begin to average. So right now, I can see my hand so clearly. Now I see just the major features. So when you stand back, the information begins to blur into each other. Stand back too far, and it's blurred too much. Too close, and it's too much detail. You actually see, if you stand right like this in a painting, you see the brush strokes. The painter doesn't want you to look at the brush strokes. They want you to look at what happens when you stand back, and it blurs together in a beautiful way. Omar,
Yes.
you're so quiet. I have to come close because your voice is so small. Whisper in my ear.
So you look at the picture square, you split it many squares,
Yes.
and each one you have like what? 300 dots.
Okay, so each inch,
Yes.
300 times 300. I don't know how much that is.
Okay. So now I'm sure that you try with different numbers, a lot higher or smaller.
Yes.
So does it have an impact on your curves? Or say for this artist, if I increase the number, it's still the curve, but for the other, no.
It doesn't make a lot of difference because really that you stand back, eventually it can blur together anyway. The blurring removes all that detail. There's no point in going too high with resolution.
So for the background, it stays record no matter.
Yeah, it's very consistent. Yeah.
But I guess there is a threshold. You can have less than
No, you need a certain number, yeah, of course. Yes. Oh, yes.
What about graphs applying at the
Graphs. Graphs.
apply at the picture?
Okay, so use graph theory, use pictures, or apply what kind of graphs? You need graphs, like the edges and vertices.
Comment on a décrit les graphes aux images pour vous utiliser? Parce que vous avez quelques notions sur les graphes et les images. Ah oui.
Okay. But is there any relation between the graph that you showed and the images?
The images. So that graph that I showed is just how close the picture is to a bell curve. So if you stand close, it's not a bell curve. If you stand back, it's better. Stand back, maybe better. And then it starts to get worse. That's all the graph is telling you. How good is the bell curve depending on where you stand? What a great audience. Now, if you feel that you need to transfer from mathematics to art, this is okay.
This is time.
It's time. Claude, can we talk to you briefly?
Yes.
A career as an artist. You are an artist. I mean, what are mathematicians? What do mathematicians do? They work on things they love because they're beautiful. Am I right?
Yes.
You do it because you love it, because it's so rich, it's so beautiful. Mathematicians are definitely artists. There's no question.
Well, so as the professor, I always say, well-known thoughts, mathematics already do, because it's not only true, but it's very useful.
Yes. Did you hear what he said? Mathematics, rightly viewed, is not only the truth, but supreme beauty. Did I get it right?
Yes.
Okay.
Possible.
That's a wonderful thought. Wonderful thought. Now, the next conference, I want you to figure out the color of elliptic curves. I've kept waiting to hear what color elliptic curves are, but nobody has started to do this work. Okay.
So let's think about it one more time. So I want to say this has been a lovely conference, and I want to.
Oh, sorry, I was going to do the same thing.
You go ahead.
I want to thank our organizers for such a beautiful conference, such amazing food. Thank you, Hussein, Omar.
Yeah, welcome, everyone.
It was so beautiful. And the coffee breaks. Unbelievable, the coffee breaks. Are Omar and Omar still here? No, okay. Omar, thank you. What a great conference. And over to hell.
Maybe see you next time.
Yes.
In Morocco.
I can't wait to come back. Thank you. So, organizers, thank you so much.
So, we are back to close the session. For me, it's a great pleasure to receive you and to get the advantage to in your lecture. Of course, there are a lot of knowledge which we need. Thank you very much to share with us your knowledge in your topics. All of them are very interesting. Hope to see you in next time elsewhere or here in Morocco. You are welcome. Thank you very much for everyone, for our speakers, for all participants, for our students, for everyone. Okay. Omar? Claude. On a de préférence.
Attending a meeting in classroom, and Miyaki was the first to work on welcome, and the second oldest was invited to work, and it happened that it was me. I was the